my presentation will be very boring, but very short as well. I want my slides. I will speak about the initiative called SR. And at one previous Enogs, there was a special SR session and Egress Peering Engineering. I think I should remind you just in a couple of words about segment routing. The SR is a form of setting the path to the packet distribution in the network, and we carry this information in the packet itself. Today, we have specified, two options have been specified for segment routing in data plane. The MPLS option and IPv6 option. MPLS option is quite simple and straightforward. Segment routing is all about setting a header to every packet, which shows the segments that our packet goes through, a link, a hub, or something else. So the header, the SR header, contains all these segments, the names of all these segments. When we use segment routing with MPLS, everything looks very nicely. Our MPLS stack is the actual listing of all these segments. And every LSR processes these packets like they always do. But for IPv6, there is a special header created, which also enumerates and lists these segments. So the idea is quite straightforward in terms of backplane. As far as control plane is concerned, we need to allocate these segments, distribute them, allocate them, and allow the nodes to add headers. Now, I will speak about the actual problem that we're trying to resolve using such a solution. We have a huge system that we operate with, and we have external connection points, clients, peers, doesn't really matter. We have to select the exit point. We need to do it in a flexible way. We need to split and separate the policy and the actual implementation, which implies the use of the centralized architecture. When we decentralize this, when we centralize this not at every node, but we do it in a more central way and send it to the traffic exchanges. There may be agent sources of traffic. This solution contains three components. The first one, to do the routing in such a fashion, we need to take the external topology. We need to know our BGP sessions, our links to the peers, and send this all to the centralized control unit, which is in charge of routing. This is where we allocate the segments that I mentioned previously. We allocate them, and we need to send them to the centralized controlling unit. It is followed by the actual decision-making with the use of auxiliary information, and sending this to the nodes and traffic sources. The first step, the allocation of the segment ID. The headers that are inserted to each and every packet when we initiate SR.
In this case, we use three types of segment ID. Peer load SID, that's an ID that identifies our peer. Peer adjacency SID, SID, that's an SID that identifies our link. Why are they different? It's a standard structure. We have several SMP links, one BGP session and one peer. But we want to be flexible enough to be able to choose one of the links, one of the parallel links to this peer. So when we have two SMP links to one peer, we'll allocate three SIDs. Peer adjacency SID for one link, peer adjacency SID for the second link, and a peer node SID for one BGP session. And the third type is peer set SID. Using local configuration on our node, we can set a certain universe of peer node SIDs or peer adjacency SIDs and can refer to this universe as one thing. So those SIDs are, well, if segment routing is implemented, then SID becomes just a marker, a kind of a label. Nothing complicated. When every SID is allocated, the router programs its own database by taking this marker, which has just been allocated, and by attaching an action to it. It is removed and it is forwarded in a certain direction, to a certain destination, either to peer or to the interface, or it is balanced across the peer set members. That is what I have just said. SID is allocated when we establish a BGP session. The second bullet point, I have spoken about that as well. Peer set is not allocated automatically. For a peer set, you have to have local configuration. Next. When the egress node has allocated SIDs, it must report to the centralized controller. For this, we have a separate draft. It is a modification of BGPLS, of the BGP link state. So from the node, egress node, we will communicate this information that, well, we have those peers and we have those links, and they have this broadband and they have this SLG or that. And we also communicate they've recently allocated SIDs. In the centralized controller, routing decisions are made. The controller takes lots of different data into account. It must receive information that was transmitted from the Egress node about the SIDs and about our external topology. The controller must know what our neighbors have announced to us along the BGP route. For this, we need IBGP, so there is nothing new there, no new standards. The controller can also, or should also, refer to internal topology. It gets the information about internal topology through BGP-LS. The controller can take into account the traffic matrix. When we know that from here we need that much channel to there, anything else, current measurements of the SLAs, current performance, any other additional and current information that will help him take the right decisions. The routing decision itself is not standardized. And the last final step, the routing decision that was taken must be distributed to egress nodes. So here we're not inventing anything new. We suggest that the already available mechanisms are used. We can go to the egress node through netconf, or we can label unicast BGP 3107 policy route to it, or we can send VPN policy route, or we can even reach it with full spec or even inflow. So any means that can be used to program the routing decision on the egress node is valid. So it will not be standardized. In our document, we only list certain means, certain methods as a recommendation or for the information of the reader. Here's a prefix, and this is the MPLS stack, and that's how packets are sent from one point to another. And there is no other information that the egress node needs to know. So all of this is described in the very fresh draft. We published it only yesterday. And I guess that is it from me. Oh, yeah. One last thing. What is the benefit of this arrangement? We do not change many things. We do not require you to change the IBGP structure. We do not interfere into the configuration. We don't require special configuration. We don't ask you to. I mean, not many things change, really. You can apply this arrangement selectively, not to all prefixes, but only to the selected ones. You can deploy it where you need it. No modifications are needed on the ingress node. All the new things happen only on the egress node and on the controller. Obviously, and that's it. Thank you. Questions? Yeah, we have a question. My name is Pavel. Do you understand you correctly that it only applies to transport tunnels? The logic of the transport tunnels, and there's no change to the forwarding stack. Well, actually, at least one more label is added to. It's a label that identifies the peer, or it identifies the external link. So the usual transport tunnels stay as they are. Well, if you want to, you can keep them as they are, but it would be better if inside them you would do the same segment routing, only in an internal one. This is yeah, they are two different stories. My story integrates well with your story, so there is nothing that stops you from integrating it with your usual RSFP signal tunnels. There's no contradiction between them. Oh, fine, I understand you. Thank you. Daniel, a short question from over there. Yes, please. What is the main benefit over explicit path? RSVP tree explicit path is traffic engineering inside our network. That saying, this arrangement, it enables us to set up an external egress, the link that is between us and a neighbor. In this external path, you cannot do this. Right? Okay. Daniel, another short question. Colleagues, please state your name and organization. My question is, the standard destination routing scheme has many deficiencies, but it has an advantage. At any routing point, the decision is taken based on the most recent information. And the problem with source routing is when the packet gets information about source routing, while it travels, it is never updated because something might have happened, but it doesn't know that. But in your draft, will this be present? I mean, have you? We have worked out a workaround. If you open the draft, you will find that workaround, the tour. On every node, we can install an additional backup path when you reach the egress node, and if something has changed during that time, and you cannot forward any further, then you can sidetrack, you can step onto the alternative path, which is programmed at the end of the tunnel, in a way. But yes, generally speaking, source routing has that feature. Yes, it does. Silence now runs deeper than during the presentation itself. So does that